Topology: stretching and shrinking a figure like a rubber band. If the shape of a figure changes, can it still be considered the same figure? Euclid's Elements served as the standard for Western mathematics and science for thousands of years. Starting from a few basic axioms, Euclid's deductive method derives theorems step by step, and it remains powerful today. However, Euclidean geometry, which had been regarded as absolute truth, gradually came into question. The starting point was the fifth axiom, the parallel postulate. Once it became clear that this postulate could not be proven from the others and was an independent condition, the foundation of geometry began to shake. Mathematicians begin to ask again, what is a straight line? What does it mean for two parallel lines to meet? From these questions, a new kind of geometry emerges, non-Euclidean geometry. In this view, the sum of the interior angles of a triangle may not be 180 degrees. Properties once taken for granted are no longer absolute. While geometry undergoes this shift, another line of study develops from a completely different perspective. It focuses not on size, such as length or area, but on how figures are connected. This field of study is now called topology. The first to discover this concept was the brilliant mathematician Leonhard Euler. In the 18th century, a large river flowed through the city of Königsberg, and there was an island in the middle of the river. To reach the island, one had to cross one of the 7 bridges connecting it to the surrounding areas. A question then arose. Is it possible to cross each of these 7 bridges exactly once and return to the starting point? Although the problem appeared simple, it was not easy to solve. Many mathematicians attempted it, but none could find a definite answer. Euler changed the direction of his thinking. He ignored the length and shape of the bridges and kept only their connections. In this problem, the key question was how the bridges were connected. Information such as length or position was not necessary. Euler represented the 4 land areas separated by the river as points, and the bridges between them as lines. The complex problem was reduced to a simple structure. He then discovered an important fact. If the number of lines connected to every point is even, it is possible to return to the starting point. However, in the case of Königsberg, every point had an odd number of lines meeting at it. Therefore, the condition could not be satisfied, and the problem had no solution. Now consider the perspective of topology in a simpler way. Think of a triangle made of a rubber band. This rubber band can be stretched or shrunk. Its shape can change continuously, but as long as it does not break, it remains a single connected figure. Then how can this triangle change? As its shape is altered, it may look like a quadrilateral, become a circle, or even take the form of a heart. What defined what was called a triangle until now? Are these figures different, or are they the same? Consider one more idea. What happens if a rubber band is cut and stretched out? Is the resulting figure the same as the original triangle? A key criterion appears here, the essential shape of a figure. A triangle made of a rubber band has a hollow structure. That is, it is a figure with a hole. When the rubber band is cut and opened, the hole disappears. The criterion for distinguishing figures is therefore not length or angle, but the presence of a hole. Topology is the field that studies the essential shape of figures in this way. For this reason, topology is also called rubber sheet geometry. From this perspective, a coffee cup with a handle and a donut are classified as the same figure since both have one hole. In contrast, a pot with 2 handles has 2 holes, so it is classified as a different figure. Then, where is this idea used in practice? A clear example is a subway map. In a subway map, the distances between stations and the curves of the lines are not important. What matters is which stations are connected and in what order. For this reason, even though it is simplified and differs from a real map, It allows quick identification of destinations and easy recognition of transfer points. In the end, topology studies not shape, but the unchanging structure of connections.